You've probably heard that quantum computers are going to solve these huge, impossible problems, right? But how do they actually do it? Well, today we're going to pull back the curtain. We're going to build a quantum circuit from the ground up, step by step, so you can see exactly what's going on under the hood. All right, so let's just jump right in with the big question, the central puzzle. We all get how regular computers work, with their simple ones and zeros. But how in the world do you write instructions for a computer that plays by a completely different, kind of weird set of rules, where a single bit can be both a 1 and a 0 at the exact same time? That's the challenge we're going to tackle.
And to figure that out, we have to start at the very beginning with the fundamentals. Just like an architect needs a blueprint before they can start building, we need to understand the absolute basics of the design.
So that blueprint, it's called a quantum circuit. And honestly, the best way to think about it is like a recipe. Your ingredients are your quantum bits. We call them qubits. And the instructions in the recipe, what you actually do to those ingredients, those are called quantum gates. And that's it. A sequence of gates acting on qubits is the absolute core of every single quantum computation. Now, any good recipe needs a place to do the work and a place to put the final dish, right? A quantum computer has two kinds of notebooks for this. First, there's the quantum register. Think of this as your workspace, your messy kitchen counter, where all the quantum weirdness is happening. Then you have the classical register. That's the clean, final answer sheet where the concrete result gets stored after you take a measurement. Okay, so we've got our blueprint and our workspace. The next logical step is to look at the simplest instructions we can possibly give. What are the basic moves for just a single qubit? Well, there are two fundamental moves you really need to know. First is the X gate. Super simple. It's just a flick. It turns a 0 into a 1 and a 1 into a 0. But then there's the H gate, or Hadamard gate, and this is what makes quantum computing so quantum. It's the superposition maker. It takes a definite state like 0 and puts it into this fuzzy state of being both 0 and 1 at the same time. This single move is what lets a quantum computer explore a huge number of possibilities all at once. So manipulating one qubit is cool and all, but the real power, the secret sauce of quantum computing, comes from making them work together. And this is where we get into one of the most famous and frankly weirdest ideas in all of physics, entanglement. The tool we use to create this quantum teamwork is called the CNOT gate. And the name says it all. It's a controlled NOT gate. This means one qubit gets to be the control, the boss basically, and its state determines whether another target qubit gets flipped or not. This is how qubits start to influence each other. And with that one tool, we can follow a really simple recipe to entangle two qubits. First, you start with two qubits, both just set to 0. Second, you use that H gate we just learned about to put the first qubit into superposition. And finally, you link them up with a CNOT gate. The first qubit is now the control, and the second is the target. That's it. You've just created entanglement. Now, this simple recipe creates something famous called a Bell state, and this chart shows the incredible result. When we measure these two qubits, we only ever get two outcomes. Either they are both 0 or they are both 1, each with a 50% chance. Notice what's missing? We never get a mixed result like 0-1 or 1-0. Their fates are now perfectly linked, no matter how far apart they are. That is entanglement. Okay, so we've built this tiny 2-qubit circuit and created entanglement. Pretty cool. But why does this matter? Let's zoom out to the bigger picture and see how these simple circuits become the engine for really powerful algorithms. Here's the crucial point. These small circuits are the building blocks, the subroutines, for everything else. Superposition lets a quantum computer explore many possibilities at once. Entanglement allows it to find complex, hidden correlations in problems. And those conditional gates, like the CNOT we just used, build the logic that ties it all together. You combine these fundamental pieces in clever ways to create powerful quantum algorithms that can tackle things classical computers could never even dream of. We've actually covered a lot of ground in a really short amount of time, going from a single qubit all the way to an entangled pair. So let's do a quick recap of everything we've put together. So here are the key takeaways. A quantum circuit is simply a recipe of instructions, called gates, for qubits. We saw how simple gates like X and H can flip a qubit or put it in superposition. Then we used a multi-qubit gate, the CNOT, to create entanglement, a uniquely powerful quantum resource. And finally, we saw that these simple circuits are the absolute foundation, the Lego bricks for all complex quantum algorithms. Of course, understanding the theory is one thing, but the real key to truly mastering this stuff is getting your hands dirty, actually building these circuits yourself and seeing what they do. That hands-on experience is everything. So I'll leave you with this thought. You now know the basic grammar of quantum computing, the gates, the qubits, and how to link them. If you had the power to build your own quantum algorithm right now, what's the first problem you would try to solve?